7.6, which is about the concept of expected value. Okay, so let's begin. So we have section, if I can adjust this a little bit. Okay, that's better. Section 7.6, which is the very important topic of expected value. Okay, so what is expected value? Basically, we have been talking about probability, which means really we've been talking about random events. So if any outcome is not random, if we have values that are not random, how do we calculate their average? So we simply take those numbers, add them together, and divide by how many values we have, right? That's the average of regular numbers, numbers that are not the result of any random experiment. But since we've been talking about probability, which means we've been talking about random events, then how do we calculate the average of random events? Well, it turns out that the way we calculate this average, which is called average of random values, which is called by the name expected value, because it's what we expect to happen, but it may or may not happen, is the way we calculate this is by we take each value, multiply it by the probability it has, and do the same thing for all the outcomes, and then add them all up together. So that's how we take into account the randomness into calculating the average of random values, that we take each value and we multiply it by the probability it has, because that value is not given. It's not that that value will occur, but it will occur with a certain probability. We multiply the value by the probability. We do the same thing for all the values we've got, and then we add them together, and that number is the average of random events, which we call expected value. Okay, so it's something we expect, but it may or may not happen. So let me write down everything that I've said in a summary form. So expected value is the mean or average of a series of random values. And I will write this with a different color, where there is a probability associated with each outcome. That's the key point, that expected value takes into account that probability. So that's everything explained in plain English. Let's write that in symbolic form. Okay, so we want to let I represents 1, 2, 4, and so on. Right, so these whole numbers, and let this notation, lowercase e sub I, is the value of event I, and p sub I, p subscript I, e subscript I, is the probability of event I. So that there is an event I, and there is a probability associated with that same event, and then E, let's take E as the letter to represent expected value. Okay, so then we can write that E, that's the expected value, is equal to the event 1 times the probability of event 1 plus event 2, the value of event 2, right, times the probability of event 2 plus the event 3 times the probability of that event plus all of that. So E sub I times probability of event I. I say I because we don't know how many events we have, but we know that that's how we calculate the expected value. Take each value, multiply it by its probability, and do the same thing for all the values and add them together. Okay, let me just add as a note here that the expected value or the average of random values is the most likely outcome, let me say, since I said value, is the most likely value in a random experiment. I hope between what I said earlier and what I've written down, you fully understand what expected value is. Okay, so let's see some examples as usual. Suppose we have some kind of a raffle. So the first prize is $100, and there are two second prizes of $50 each, and 5 third place prizes of $10 each. So Alexis buys one ticket, and we want to know how much more than the expected value of the ticket did she pay. Value of the ticket did she pay. Okay, so we know how much she, Alexis buys one ticket, okay, and they're purchased at $1 each, all these raffle tickets. So we know she paid $1, but then we have to know, to answer this question, we need to know how much is the expected value of each ticket, and then we can compare and say, okay, she paid less or more. We can determine that later. Okay, so first, let's see what is the outcomes, what are the values of these, the outcome in of each ticket, and what is the probability of that outcome occurring in order to calculate the expected value, right? So first, let's calculate the expected value. So we have, according to the description of the problem, we have tickets. We have one first prize ticket that wins $100. Then there are 2 second prizes that each have win $50. And then a third prize, there are 5 of those that each of them will win $10 each. Okay, so let's put that in some kind of an organized way. So winning ticket, we have one ticket that may win $100, right? $100. And that's because it's one ticket. What is the probability of this happening? This is we have 1,000 tickets, and this is one ticket that wins that much. So the probability of that happening is 1 over 1,000, right? Or 0.001. Okay, so what is the other possible winning outcome or winning ticket? We have 2 second prizes of $50 each. So these are $50 tickets, and there's 2 of them. So let's multiply that. Because there's 2 of them out of 1,000, so the probability of this happening is 2 over 1,000, or 0.002. Right? No, sorry. So this is, yeah, that's correct. So that's the probability of that happening. And then the third place ticket, each of those wins $10, and there's 5 of those. And what's the probability of that happening? Winning one of these tickets that wins $10 each. There's 5 of them, so 5 over 1,000, or 0.005. Okay, so those are the only possible winning outcomes and their probabilities. So the expected value of playing this game is simply multiply each type of winning by its probability of occurring. So $100. So 100. Let's see. So 50 times. Okay. So $100 has probability 1,000 plus the $50. Oh, these are dollars. So $50 times the probability that it may occur, which is 2 over 1,000, plus, I'm running out of room, but maybe I can fit it here. And $10 tickets that has probability of 5 over 1,000 of being won by somebody. Okay, so let's do the algebra or arithmetic on this. This will be 0.1. This will also be 0.1 plus 0.05. That's that one. And that will be $0.25. That's the expected value of a ticket. It has that much expected value on average. Okay, so according to what Alexis did, she bought just one ticket and paid $1 for it. So expected value is that. And Alexis paid $1 or $1 like that. So then 1 minus 0.25. So Alexis overpaid that much. Paid this much over the expected value. Okay, So that's how we calculate that. Let's do another example. This time we have two people that are participating in a game, and we want to know what is the expected value to each player, because it could be different depending on how they're playing the game. Okay, so and Sally. So there are two people who are playing this game, and we want to know what is the expected value to each player. So there are two, we are told that two teams have played each other 14 times. Team A won 9 games, and Team B won 5 of those games. So think about the significance of that information as we are going to calculate the expected value of the game for these two players. Think about what significance that information has, right? You can pause the video and come back to it and then and see what answer I have. Where I'm assuming you've done that. So the significance of that is that now we know the probability of Team A winning the games between A and B, and Team B winning the games between the two teams, right? So let's calculate that. So because in the end we have to calculate the expected value of playing this game for any player. So probability that Team A will win, according to the data that we have from these two having played each other in the past, so it will be 9 out of 14. And probability that Team B will win, it will be 5 of those games out of 14, right? So that's the probability of each team winning from the past data. So they will play again next week. Great. So Bob offers to bet $6 on Team A, while Sally bets $4 on Team B. The winner gets $10. What is the expected value of playing this game for Bob and Sally? Well, the expected value of playing the game is the $10 that we know they will get if they win, times the probability of that team winning, right? So for Bob, so for Bob, these are the, so Bob bets on Team A, right? Bob bets on Team A, yes, on A. Sorry, this is a little bit crowded there. I should have had more space. So, and Sally bets on team B, right? So what is the expected of playing, what is the expected value of playing this game? Well, it is the $10. That is the outcome of playing that game, if he wins, times the probability of winning. So 9 over 14, and what do we get? We get $6.43. That's the expected value to Bob. And Bob bets $6. Bob bets, let me add that there, please. Bob bets $6 on team A, and Sally bets $4. This is according to the information given to us in the bets. And Sally bets, it's up there. So Bob bets to bet that much. That's Bob bets that much, and Sally bets $4 that much. Okay, so Sally bets $4 there. Okay, so for Sally, that would be $10 winning if she wins, with probability 5 over 14, which is, let's see, that would be $3.57. Yes, okay. So that's the expected value to each player. So expected value to each player, right? We know that. So the other question you can ask about this is to whom, Bob or Sally, this game is fair. Or so let's call this part A, and let's call this part B, and we say to whom Sally or Bob is the game fair. I mean, this is an extension of our expected value calculation, right? But we can answer this question given that we know what the expected value is to each player. Well, for Sally, is the game fair? Well, no, because so Sally, expected value of playing this game is $3.57 to Sally. But she paid $4. She bet $4. So even if she wins, the expected value is less than what she's betting. So because $3.57 is less than $4, which Sally bet, the game is not fair to Sally, is not fair. Okay? But the game, let me just say, but by the same token, but the game is fair to Bob, because what he paid to what he bet to on the game, $6 is less. Let me go to the next page, because what Bob bet on the game is less than the expected value of the game to him. Okay, and of course, the two bet on different teams. One of them had a higher likelihood of winning, and that's why the game is fair to Bob, given how much he bet and which team he bet his money. Okay, so let's do another example. Hopefully as you watch these, you make a note of, hopefully you review these, and then if you still have questions, you bring them up during the discussion board sessions where everybody can benefit from your questions. Okay, so we have a data here. So the following data I should say this is randomly collected data. So the following randomly collected data it shows the expected transportation and collected amounts, or collected amount from each at a toll booth across a bridge, across a bridge. So given this data, which I will list, given the data, what is the expected value or expected let's say expected amount collected at the toll booth during the peak hour in the future, on any day in the future, on any day in the future. So what I should have mentioned earlier is that this data was collected during the peak hour on a few days in the past, and then it was averaged somehow, and now we have it. So let me see where I can insert that. Expected types of collected and collected amount from each at a toll booth across the bridge during peak hour. During peak hour traffic. Okay, so let me add that. So this was in the past. This happened in the past. Now we're trying to use this to say something about the future, the upcoming days. Okay, and that's why we call it expected, because the previous data was random. Now we'll use the random data to make a conjecture about the future, the expected collected fees during the peak hour in the upcoming days. Okay, so here's the data. We have so type of transportation, and then we have total toll collected, and the probability of that kind of transportation going through the toll booth at this bridge or crossing this bridge. Okay, so that's the probability for each type of transportation. So this would be heavy trucks, and then 2 would be buses, and number 3 would be cars, light trucks, SUVs, and such. Cars, trucks, SUVs, and finally, so what else we have left? Motorcycles. Okay, so we have that kind of the data broken up into those categories, and then the total toll collected from each category in the past on any given day randomly. Here it was $1,020. For buses, it was $180. For cars, trucks, SUVs, and these are during peak hour, right? So this was just whatever the peak hour must have been at this crossing over this bridge, maybe 2 p.m., maybe 4 p.m., maybe 9 a.m., we don't know. But this data is for the peak hour traffic. And then $7,200 from cars, trucks, and again $180 from motorcycles. All might have been 10 motorcycles, 20. All that information is hidden, but we just know the type of transport, how much was collected during the peak hour from each type of transportation. Now, the Department of Transportation must have probability of each kind of transportation going through this bridge during the peak hour. So those probabilities are as follows. We are given those probabilities: 0.0624, and then 0.013206, 0.8804, and 0.04402. Okay, so now, given the data, what is the expected amount collected at the toll booth during the peak hour on any day on any day? I should have said just on any day. Doesn't matter in the future or in the past. It just gives the expected value, gives us an idea about what we might expect during peak hour collection from this crossing. Okay, so simply we will take each of these total tolls collected from each category, multiply by the probability of that, and we have our expected amount for the peak hour. So let's do that. So we have 1,020 times 0.0624 plus 180 times 0.013206 plus 7,200 times 0.8804 plus 180 times 0.04402. Please double check this final number that I'm going to write down. I don't know if my notes are not. I have a lot of scratch marks on my notes, so I'm not sure if some of these numbers are. For example, that number, I'm not sure what I have on my notes. But please double check, and it should check out to $6,412.83. Just this much toll we can expect to collect on any given day across this bridge during peak hour. So if you collect the data, say around midnight, which probably isn't during the peak hour, then you probably get very, very much a value, an amount that is much, much less than this, maybe even less than 1,000. Okay, all right. So that was another example. Let's do another example. So we have a 20-year-old female who purchases an insurance policy. And the policy is worth $250,000. Right? And the insurance company, determines that she will survive the policy period with this probability, this 0.9995. Right, so this is a very high probability of her surviving the insurance, the policy period, which is that 1 year for which she purchased this. Of course, this is high because she's very young, right? She's only 20 years old. Okay, so, and given this information, if the premium for a policy is the amount you pay to purchase a certain policy. That's the premium. So the premium for the policy is, let's suppose if it's $300, the question is, what is the expected profit for the insurance company? Okay, so as before, when we talked about, when we were discussing revenues and break-even scenarios, and even with other examples, we remember that profit is revenue minus cost, right? If you've taken the accounting course, Accounting 101, so profit is equal to revenue minus cost, right? We know that from accounting. Now, this is expected profit, right? So we have to adjust. So expected by the same token, so because of that, expected profit is equal to expected revenue minus expected cost, right? So we're adjusting the same formula for the expected profit. Now, as soon as we add this expected word before each part of this equation, we are introducing the probability of that element happening, right? So we're no longer certain about the profit. The profit now has an expected profit. It may or may not happen. The same thing with revenue, the same thing with cost. So this adjustment has to happen. How? With the way we incorporate the probability for the revenue for this insurance company and the cost to this insurance company, right? The probability. For example, what is the probability of the expected value of the revenue? Okay, the revenue is that the customer brings this much, pays for the premium. It pays for the premium, and that's the revenue for the company. And that revenue has a probability of staying with the company, and that probability is equal to the probability of this policyholder surviving the policy period. And then what is the expected cost? Well, expected cost, if heaven forbid, if she loses her life during the policy year, then the company has to pay a certain amount to this client. So that will all have to be the cost side of the equation minus what the premium purchaser or the policyholder paid as premium to purchase this policy. Okay, so let's see how we can calculate the expected profit. So we have the revenue piece. Well, let me put this here. So expected revenue is the $300 that she paid for the policy. Let me see that one. If the premium for the policy is $300, so that's how much she paid to purchase it, if she survives it with this probability, that becomes the permanent revenue for the company. The revenue for the company. So then so this is expected revenue. Well, let me put this in pieces. I think that's a better way of explaining this. So expected revenue, of course, all of this is for the company, right? Expected revenue for the company, insurance company, is $300 with the probability of 0.995. So the insurance holder or the policy holder survives the policy period, and the company collects the $300 with no cost to the company. That's all revenue with this probability. So because if it's expected revenue, we have to include the probability of that amount staying within the company. Okay, 300 times that, we get $299.85. That's the expected revenue, not the actual revenue. Okay, so then the expected cost is whatever the company has to pay out, and with a certain probability. So what the company has to pay out, that's in case the policyholder doesn't survive that period, right? The entire money that comes out of the pocket of the insurance company is $250,000 $250,000 minus the $300 that the policyholder brought in. So that much. So if she doesn't survive the policy period, then whatever in addition to the premium is what is leaving the company's pocket, right? That's the net cost to the company. And what probability does it have? It's complement of that. So if that's the probability of the policyholder surviving the policy period, then 1 minus that is the probability of her not surviving the policy period. So that is equal to, let's see if I have that number written someplace. I do. So that is $124.85. Okay, so expected profit then is these two values subtracted from each other. Expected revenue, which was $299.85, minus the $125.85, and this will give us how much? We will get $175. That is the expected profit to the company. Okay, $175. So let's suppose that the company would like this expected profit to increase to some higher value, let's say $250. Okay, that's the next scenario, part B. And we want to know what should the premium change to if we want to increase this expected profit to another value. Okay, so let's do that. So that will be part B. Okay, so part B. Such that expected profit will be $250, right? So we know that when the expected profit was $175, the policyholder paid $300. So now this turns part A on its head and asks the question the other way around. If we want to have the expected profit to be this much, so now we know how much expected profit we'd like, then how much the premium should be set at in order for the expected profit to increase to $250. Okay, so this is a calculation of something that many of you might find obvious, but I mean the answer, once we get to it, it's going to look obvious, but it's because these probabilities are so near 1 on one side and so near 0 on the other side. But let's take a look at it in a few seconds. Okay, so now we have the same thing, expected profit equals expected revenue minus expected cost, right? That's what we used. So this time we know what this is. We're not looking for it. We know that this has to be $250. Expected revenue, now this is a whole new ballgame. Let me bring back the previous slide. So we're looking for the premium, right? That's the unknown. In the previous slide, in the expected revenue, the premium was $300. For this scenario, it'll be X. So X times the probability that the policyholder survives. This same policyholder, right? So which is a 20-year-old female policyholder. So instead of, in our equation, instead of 300, we're looking for this value because we don't know what the premium should be yet. So that'll be X times this probability for the same person, which would be 0.9995. Okay, then minus, well, if you like, let me do this the same way. No, let's combine it. It's better to combine this. Okay, so minus expected cost. Expected cost, in the previous case, we calculated it using this relationship. In here, again, this is the premium. So let me write that here, premium. So in part B, we're looking for that. So in my equation there, I should have 250,000 minus X times 1 minus that, which happens to be 0.0005. But I'm going to list the same thing so it doesn't confuse anybody. But this number is 0.0005. Okay, so let's write that down. We have 250,000 minus X times 1 minus 0.9995. Okay, so in this equation, we're looking for the value of x. All right, so we have 250 equals, let me see, I'm looking at my numbers here, so 0.995x, okay, so 0.9995x, right? And minus, this is 0.0005. So distributed to 250,000, multiplying 0.0005 by 250,000 and distributing the negative into it, we get minus 125. And then 0.005 times x, distribute this negative into it, we get positive x. So positive 0.0005x. Okay, so then we have 250 equals this plus that, we get just x, right? 0.9995x plus that is just x, 1x. Add these two, you get 1x. Minus 125. Then move this to the other side. Oops, 250 plus 125 equaling x. So x would be equal to $375. So this should be the premium or what the policyholder will pay if the company would like to have a $250 expected profit from sale of this policy, of course. Okay. Please bring your questions to the discussion board on this topic. So let's do another example. So here's the clue once again, that she expects the following returns. So it's important to notice that each of these is the expected annual return. So maybe I should highlight that. So this is not only the annual return of that much, but it's the expected, this is the key word, expected annual return of 25% from Boeing stock. For Apple, we have the expected annual return of 18%. For Aetna, the insurance company, right? The Aetna. We have the expected return, annual return of 8%. And from the Caterpillar, we have an expected annual return of 10%. So given this information, okay, so in this example, we have an investor who decides to create a portfolio that initially will contain 4 stocks, and these are the stocks, and she expects the following returns from the stocks. And for part A, we're being asked to calculate, okay, if she invests equally, that's very important. If she invests equally in all stocks, what will be her expected, and that's of course the key word here, the expected annual return on the portfolio. So we've already talked about the expected value being the probability of some outcome times the value of that outcome, right? But in this case, the annual return, the total annual return, will comprise of the expected annual return coming from each of these stocks, right? So each of these expected annual returns in effect becomes the probability of that kind of earning. So we have, and by the way, in this case, notice one key piece of information that is missing, which by the way doesn't matter, is how much the investor is putting money into these stocks, right? They don't tell us how much. They don't tell us if it's $5 or if it's 10 million or if it's 100 million. We don't know. But the fact that we are told that she invests equally in all these stocks makes the total amount being invested irrelevant. Because we know whatever that amount is, 25% of it will go into Boeing, 25% will go into Apple, 25% will go into Aetna, and 25% will go into Caterpillar, right? 1/4 of the total amount, whatever it is going to go into each of these because she's investing equally in all the stocks. So for the sake of ease of our calculations, since it doesn't matter what the investment amount is, let's assume that she's investing $1 single dollar. Okay, let's do that. So we're going to make that assumption that assuming that $1 was invested, then each stock receives only 25 cents, right? $0.25 or 25 cents. Okay, so the expected value then, let me try to keep this on the screen as much as I can, like that. So the expected annual return in this case would be 25 or 25 cents or $0.25 amount, 0.25 times the expected annual return. Okay, the expected annual return, which is 0.25, we got to convert those to decimal form, plus the next 25 cents or $0.25, which would be invested in Apple stock, right? And that has an expected annual return of 18% or 0.18, plus the next 25 cents or $0.25 times the stock, the annual percentage return from the stock it's going to be invested in, which would be Aetna in this case. So 8% would be 0.08, right? Not 0.8, but 0.08. And then let me, because I'm running out of room there, so let me put that here. Then the last 25 cents or $0.25 times Caterpillar's stock has an expected annual return of 10%, so that will be 0.1, right? Okay, so let's make that clear that this is for Boeing. This is the expected annual dollar return on the Boeing stock. This one is for Apple. This one is for Aetna. And of course, this one is for Caterpillar. Right? Okay. So therefore, we have the expected annual return as follows: 0.0625 plus 0.045. So please double check my numbers here. Hopefully you'll agree, your numbers agree with mine. Like that. And of course, E would be 0.1525, or let's convert that to percentage. So the E would be 15.25%. That would be expected annual return from the entire portfolio, which comprises of these 4 stocks. Okay. So that was part A. There's a part B to this question. Let's go over that also. So here, basically, part B is talking about the investor choosing a different strategy. Okay, and then we'll have to calculate how much she should invest in 2 of the stocks, and you'll see. But it's a different strategy of investment. Okay. So as you can see, her strategy of investment is changing. So this time she decides to keep half of her investment evenly split between these two stocks, right? And again, they don't mention how much she's investing, but that doesn't matter. If you just assume out of $1, half of it is evenly split between Apple and Aetna, that means of every dollar, 25 cents will go into half of it, will be evenly split, right? So the 50 cents out of a dollar, it's going to be evenly split between Apple and Aetna. So 25 cents will be invested, 25 cents of every dollar will be invested in Apple, and 25 cents of every dollar will be invested in Aetna. And then, how should she divide, the question they're asking, how should she divide the remaining half of her investment? That means the other 50 cents. Between the other two stocks, that would be the Caterpillar and the other one, Caterpillar and Boeing, right? How should the other 50 cents be divided between the stocks for Caterpillar and Boeing in order for her to realize an annual return of this much, 17.75%? Remember, the strategy that she had in Part A, that one, gave her a 15.25% expected annual return, right? That was coming from strategy used in Part A. But now that she's changing strategy, we need to know how much should go into Boeing stock and Caterpillar stock, these two stocks, right? The previous strategy was that out of every dollar, 25 cents should go into Boeing, 25 cents into Caterpillar. But that would not get us to where she wants to be, right? She wants to be at a higher annual percentage rate. So to bump this up to 17.75%, we want to know how much should be invested in Boeing and how much should be invested in Caterpillar. So these two are the unknowns. These two values are the unknowns. Okay? The expected annual return from Boeing doesn't change. It's still 25%. The expected annual return from Caterpillar is not going to change. It's still 10%. Okay? But we want to know how much of every dollar should be invested in Boeing and Caterpillar in order to help her realize a higher expected annual return. Okay, so that's the question. So this time, in order to set up the equation, we begin with this. In Part A, we were looking for the average expected annual return. This time it's being given to us. We need to work backwards and find how much of every dollar should be invested in Boeing and Caterpillar. So we will begin with that. Becoming 0.1775, right? In our calculations, we need to convert everything to decimal form. Okay, so for the knowns, we already know that 25 cents of every dollar, or 0.25, should go into Apple and then the same amount into Aetna. So let's write that down. We have 0.25 times 0.18. That's the expected annual return from Apple. Okay, so this is Apple in this new strategy, right? Plus another 25 cents times 8% or 0.08, and this is the strategy for investment into Aetna this time. Then we want to know how much should go into Boeing and how much into Caterpillar, right? How much of the remaining 50 cents on a dollar should go into each of those stocks. So let's call that X dollars. And as soon as I introduce a variable, I'm going to need to define that. So let me define that up here. I'm going to define that as X being dollar invested in Apple. Boeing. Let's define it as that in Boeing. Okay, so that's that. And what was the expected annual return from Boeing? It was 25%, right? Right there, 25% from Boeing. So X dollars times 0.25, and then plus, so let me label this. This is the how much that we're looking for to be invested in Boeing. Now, how about Caterpillar, right? So we already know the 50 cents on every dollar should be evenly distributed to Apple and Aetna in this new strategy. Of the remaining 50 cents, X amount of it should be invested in Boeing, which we're looking for. So how much should go into Caterpillar? Out of every dollar, we're dealing with just the 50 cents. That is going to be the split between Boeing and Caterpillar. We're looking for that. So we're looking for how much of every 50 cents on a dollar should be distributed as such. So we took X as being the amount that is going to be invested in Boeing stock. So out of every dollar, the 50 cent, then how much of it should go into Caterpillar then would be basically 0.5 minus X times 0.1. And 0.1 being the 10% expected annual return from Caterpillar. Okay, so out of the 50 cents that is left to be split between the Boeing and Caterpillar stocks in this new strategy, we want some of it, which we don't know yet how much of it, we take that as X, should go into Boeing, and then the remaining of that 50 cents on a dollar, so 0.5 minus X, should be invested in Caterpillar. Okay, so let me label this for the sake of clarity. Caterpillar, right? Okay, so this, in effect, this becomes an equation in X, one equation, one variable, and we can easily solve it, right? So let's do that. And please double check my numbers with your own calculations. Let me move this into view here. So we have, if you multiply these, you should get 0.045 plus, and then multiply 0.25 by 0.08, and hopefully you get 0.02 plus 0.25x, right? And then this 0.1 should distribute itself into 0.5 and then distribute itself into minus x, right? So 0.1 times 0.5, we will get 0.05, right? And then minus 0.1x, right? Just distribute 0.1 into these two, and you should get these two last terms in the equation. Okay, so we have x here, we have an x term here, and an x term here. On the right side, let's combine all the constants and let's combine all the x terms. What do we get? So we're going to get, if you add 0.045 plus 0.02 plus 0.05, you should get 0.115, and then add 0.25x, and I should say subtract because we have minus here, so 0.25 minus 0.1x should give us plus 0.15x, right? Just subtract the coefficients, and we get that. Then the rest is just basic arithmetic, right? 0.1775 minus 0.115, right? We move this to the left, it becomes negative as we do that, 0.15x. And then next we have 0.0625 equals 0.15x. And then finally, if we divide to calculate x, we have to divide both sides by 0.15, right? So 0.0625 divided by 0.15. And then from this, the result is that x should be 0.4167. Okay? So what is the result that we get from here? So let's round this up, because this is about dollars and cents, and to make it easier, then let's round this to 42 cents, right? So this would be, and this is in dollars, or about 42 cents. So this would be about 0.42 dollars, or 42 cents. Okay, so this should be invested in Boeing, right? That was the X, the amount of every dollar that should go into Boeing stock. So out of the 50 cents that we had left, then 42 cents of it should be in Boeing. Right, should be in Boeing. So how much of it should go into Caterpillar? Simply subtract 0.42 from 0.5, right? We get the amount that should be invested in Caterpillar. So then, and I will write down the conclusion at the end, but we have 0.5, which is the 50 cents on every dollar. Subtract from that the 42 cents, and we get 0.08, let's say almost, that's the symbol for almost, or approximately. 8 cents should be in Caterpillar. Okay, so the ultimate strategy then would be as follows. We say that, so this is our conclusion. We say put about about 42 cents, or 42% of every dollar, right? We can do this because every dollar is comprised of 100 cents, right? So it makes it easy to convert this amount of every dollar to percentage. Okay, so 42% of every dollar into the Boeing stock, and the remaining, which is the 8 cents, and put about 8 cents, or 8% of every dollar, into Caterpillar stock. Of course, this is this proportionate amount from every dollar can be translated to any amount, right? So if it's $1 million or 100,000, it's 8% of that $1 million or 100,000 should go into Caterpillar, 42% of it should go into Boeing, and the remaining 50% should be evenly divided between Apple and Aetna. Okay, I hope this, so this is the ultimate conclusion for this problem. So I hope this helped make sense of the expected value, which is an important topic in probability and statistics. So this brings us to the conclusion of section 7.6, and I'm thankful to you for persisting through these videos, and for now, have a nice day, and I'll see you again next time.